The rise of underwater data centers, China's pioneering leap. The rapid expansion of data-intensive services, especially AI, is colliding with ecological, spatial, and energy constraints that challenge the sustainability of traditional land-based data centers. Underwater data centers present a pragmatic alternative: sealed, modular server pods deployed to moderate depths that use the ocean's stable temperatures for passive cooling, reduce land use, and enable closer edge connectivity. Recent commercial deployments in China convert a once experimental idea into an operational model with measurable energy and water savings, while exposing novel engineering, environmental, regulatory, and security questions that must be addressed as the sector scales. The underwater data center concept emerged from three interacting pressures: the high and rising energy cost of cooling, scarcity and cost of near-urban land, and surging demand for low-latency computation. By situating sealed server modules beneath the sea, operators exploit ambient seawater as an efficient heat sink, substantially reducing or eliminating HVAC systems and evaporative cooling that consume electricity and freshwater. The model also favors prefabrication and modular expansion, allowing pods to be assembled onshore, rapidly deployed, and networked via subsea fiber and power cables close to coastal population centers. China's deployments off Hainan and Shanghai mark a turning point from pilots to commercial operation. Key characteristics of these projects include scale and ambition. Initial Hainan units measure roughly 18 meters and weigh over 1,000 tons, with plans to scale into multi-pod subsea estates capable of matching large terrestrial clusters. Integration with policy. Projects operate inside special economic zones and benefit from subsidies, relaxed ownership rules, and strategic alignment with national, blue economy, and decarbonization goals. Renewable linkage. The Shanghai Initiative ties seabed computing to offshore wind, sourcing the vast majority of operational power from nearby wind farms. Commercial uptake. Early contracts span cloud services for hospitality and travel, e-commerce, and AI workloads, demonstrating viable revenue models beyond research demonstrations. China's approach differs from earlier trials by prioritizing rapid commercialization, direct coupling with subsea cable landing stations for optimized latency, and coordinated public investment that absorbs early engineering risk. Underwater pods demand specialized engineering that addresses pressure, corrosion, biofouling, and long maintenance cycles. Structural design. Cylindrical, pressure-rated hulls built from high-grade steels and advanced alloys provide the mechanical basis for deep deployment. Surface protection. Long-lived glassflake epoxy and similar coatings dramatically reduce saltwater penetration and biofouling, extending maintenance intervals. Internal atmospheres. Dry, inert gas fills reduce oxidation and permit electronics to operate with lower failure rates. Modularity. Each pod functions as a semi-independent node connected by high-capacity power and fiber lines, enabling phased scaling and targeted retrieval for upgrades. Maintenance ecosystems. ROVs, elevator links to surface structures, and AI-driven predictive monitoring minimize human dives and enable remote operations, though full retrieval and physical upgrades remain logistically intensive and costly. These design choices underpin the large reductions in cooling energy and hardware degradation reported by pilots and early commercial sites. Underwater data centers offer a practical, high-impact lever to reconcile growing computational demand with energy and water constraints. China's commercial deployments demonstrate that the model can move beyond pilot projects into revenue-generating, renewable-linked infrastructure. Realizing the promise at scale requires rigorous engineering, sustained environmental monitoring, resilient network architectures, and coordinated policy frameworks. If implemented with precaution and transparency, subsea computing can materially reduce the environmental footprint of data storage and computation while reshaping how and where the world's digital backbone is built. The oceans will not be a simple solution. They will be a complex frontier demanding interdisciplinary stewardship commensurate with the scale of the benefits and risks involved.